there's a tremendous amount of complex calculations taking place here, not just to fly a helicopter, but to fly a helicopter in the disturbed air that occurs following a ship to land on the platform. Can you talk about what you've done here and why this is such an exceptional model?
Basically, it is a very challenging problem, and there are lots of people around the world trying to tackle this and simulate it more accurately. One of my interests is high-performance computing or supercomputing. So normally to do this calculation we do need to use a very large computer, and typically in simulation those large computers aren't used. So what we've tried to do is couple a real-time flight simulator with human in the loop with a supercomputer. And that allows us basically to ramp up the fidelity of our aerodynamic model of the flow around the ship in order to improve that representation to the pilot in the simulator.
This is an extraordinary undertaking, and once again, like I said, for those of us who barely got through pre-calc, can you talk about how the industry is looking at problems like this and what's being done to solve them?
Well, one of the real things is this is the sort of problem where you don't want to try it for the first time for real. Because it's very dangerous, and you know, you could lose lives, and therefore we need to have the training device to represent it as accurately as possible. And the problem here is you don't want a negative training outcome. And so there are lots of people trying to improve the fidelity, and it really is a safety issue for this particular problem. In the broader sense, what it allows us to do is basically take the lid off what we're able to do in terms of fidelity. So not just for this problem, but for other problems. So for instance, you could do real-time stealth calculations by doing a computational electromagnetics computation in real time, and other similar problems. So it really kind of opens up real-time simulation into a whole new world, and that's what we're pretty excited about.
Now, how is this going to show up in the real world in the industry?
I think what's going to happen is a big architectural change. So moving to this type of system is going to take a few years, and this is really just a proof of concept. We're trying to do something that's almost impossible. Therefore, what we've done is we've shown that it is possible, but it's going to take a few years before it's robust enough to be implemented in a production flight simulator. As a university, that's what we do. We try and break through those barriers and then lead industry into these new areas.
Cirrus Design's Vision SJ50 single-engine personal jet offers exceptional fuel efficiency, flexible seating for up to 7, advanced avionics, and all the Cirrus safety features you expect, including the Cirrus airframe parachute system. With its detailed design, the Cirrus Vision is technologically advanced, yet engineered to be simple to fly, to allow owner pilots more lifestyle pursuits than any other personal aircraft. Learn more about the Vision SJ50 at cirrusdesign.com.
But what are the elements involved in this? If you can take us through the steps that are necessary to put together a pretty faithful model of the real thing.
Sure. Basically, what we're using is actually a computational model that we use with the Met Office in the UK. So it's a very high-resolution weather forecasting code, essentially. And what we do is we model the flow, the area around the back of the ship by splitting it up into tiny blocks. And then on each of those blocks, we solve a set of equations which govern the flow of air, except we have to do millions and millions of those calculations a second in order to get the right result. And that's the problem, really, is we need a massive computer to crunch those numbers in real time. And that is the real challenge. Whereas in a current flight simulator, you would use much more simplified equations. So they still give you a reasonable representation, but it's a big jump to do a full fidelity calculation of this order of magnitude.
Interesting. Now, how will the industry be able to field that kind of quote-unquote horsepower in regards to being able to model these things successfully?
It's really going to be for particular training applications, and it is where the problem now is that the current simulators aren't able to reproduce it. I mean, one of the things we're going to look at next, for instance, is brownout. So trying to do a very high fidelity calculation of brownout in order to improve training and also improve helicopter design. So the industry will see it in better training, but also moving it into the realm of the actual engineering and design, and maybe trying to get human-in-the-loop simulation earlier on in the design process in order to catch problems early, which will save a lot of cost and possibly also improve performance and safety as well.
Well, what other highly complex tasks might a model like this be successfully applied to?
As I said, the brownout problem is the next one that we're going to tackle, really. The brownout models at the moment are fairly limited. There are some companies that are doing a great job trying to improve those, but we think with this approach we can actually really make a step change in the capability for something like brownout or whiteout, so that's another obvious application. Another one would be trying to model nap of the Earth flying over mountainous terrain, where if you dip into a valley, it's quite quiet in terms of the wind, and then when you pop over the ridge, suddenly you get hit by a gust. So being able to model that in real time is something that we're looking at doing in the future using this technology.
You've heard of this thing called WAS, right? The Wide Area Augmentation System lets you fly GPS glide path approaches without relying on ground-based landing aids. No VOR, no ILS, no problem. Fact is, WAS is so smart, it even knows what you're going to say next time you need it. And don't have it on board. Wah! I want my WAS now! I was really crying there for a second.
Okay, so what we're trying to do is simulate the flow over the back of the ship. So this diagram shows us a cross-section of the back of something like a frigate, and we've got the ship deck here, we've got the hangar, and the flow is coming from left to right, and we get a big bubble basically behind the hangar, and what happens is as the helicopter rotor comes down, it disturbs this flow, and it's very complicated, and that interaction actually buffets the helicopter. Lots of current technology with simulators will compute the flow over the hangar and have the helicopter fly through it, but what it doesn't do is have the interaction of the rotor aerodynamics with the hangar, which is a very complex interaction. And that's what we're trying to simulate here. So that's where we have a bit of a change, where it's a true two-way data exchange between the computation of the fluids and the dynamics of the helicopter. Yeah, I'm just trying to land on the back of the ship here, and the supercomputer is going to be throwing me around a little bit, which is going to make it a bit tricky to land. So just trying to edge over the ship without getting too thrown around too much. Whoa. So just all right.